Hi, I thought that the no audio was only for the music video. I was wrong. There is a button I had to press. I am coming to you from an unusual location. I am currently in Tucson, Arizona, where I am working out of a colleague's office at the headquarters of the Planetary Science Institute. And it is a new location, a new day, a new set of technology, and hopefully things won't go too entirely sideways. We have a whole variety of science stories to bring you, and we will be bringing them to you from here both today and tomorrow. Next week, I am going to be traveling. Annie is taking time to deal with a whole bunch of randomness, because life. And we are going to take a week off of streaming. Now, if all goes as I hope it will, we will continue to bring you the podcast edition of this show. I just don't think I'm going to have the bandwidth where I am, or the, prolonged periods of peace and quiet to do a live stream for this show. So please check out our podcast edition, and you won't have to go without your daily, astronomy fix. In today's first story, we bring you news from the Andromeda Galaxy. Now, when we think of the Andromeda Galaxy, what we normally think of is that beautiful disk with the embedded spheroid of stars in the center that you can see an image with an amateur telescope, and if you know where to look, is the one object that's not in our galaxy that you can see from the northern hemisphere. The Andromeda Galaxy is fabulous, but what we normally see is just the smallest, and admittedly most massive, but the smallest part of the galaxy. The actual galaxy extends out to a much greater distance and is surrounded by tails of material. And this can be seen when we do extremely deep imaging, where we are looking for the faintest flickers of light surrounding the Andromeda Galaxy. What we're looking for can be seen best in the infrared, where hot gas gives off infrared radiation. A team of astronomers working with the 4-meter Mail telescope in Kitt Peak, right here in Tucson, Arizona, as well as astronomers working with the 8-meter Gemini telescope on Mauna Kea, were able to do very deep images of the area, covering that halo around the core of Andromeda. And in that halo, they were able to find dozens of clusters of stars. And by measuring the velocities of these clusters of stars, they were able to piece together the merger history of the system, at least some of the merger history of this system. What they found is there are multiple streams of material that are flowing in some cases at right angles to one another. And in one case, they found that the stream was filled with stars and also star clusters. And this combination appears to be, the leftover relics of a merger that took place several billion years ago. So our planet had probably formed when that merger happened, but we weren't yet very advanced. Now, the other stream that they observed in detail is one that didn't still have stars left in that tidal stream. And looking at those clusters, they came out with a model that seems to indicate that merger occurred, billions and billions, not billions and billions, but many, many billion years ago. Now, those are two very different timelines and two slightly different sets of material. And this seems to indicate these are two separate relics of Andromeda merging with objects roughly the same size as the Large Magellanic Clouds. So we're slowly piecing together the history of, the nearest large galaxy. Now, this is particularly interesting because we know our own galaxy is surrounded with these kinds of tidal tails. They usually in our system come from the Milky Way, eating dwarf spheroidal galaxies and other really small systems. Well, these are two slightly larger systems that got eaten. And this helps us understand the physics of all the things that our galaxy probably has gone through in the past. This is how we think massive galaxies like our own, that aren't too massive, were able to form through the constant buildup of one small object after another over the history of the universe. So here is to looking around to figure out how things here work by looking out there. In our next story, you never know what will happen if you get just the right combination of people in just the right place. But you can hope for what will happen. And this is exactly what happened when NASA, the SETI Institute, a variety of academic partners, and industrial partners, including the likes of Google and Microsoft, all got a bunch of early career researchers, both in the sciences and in computer science, together in one place for an 8-week technology accelerator. They provided these individuals with a variety of problems and said, go forth, try and solve things, figure out what's going on. And one of the problems that they gave was the problem of trying to figure out what the sun is doing in the extreme ultraviolet color of light without being able to look at it in the extreme ultraviolet. Right now, there is an instrument on the Solar Dynamic Orbiter that is able to take images like the one you see here. And these images show us the high energy events that are currently taking place at the sun. These are events that can affect us here at the planet Earth, causing either massive amounts of particles and radiation coming our way to do nasty things to spacecraft, or to set our Earth's magnetic field shaking and do harm to our own planet's power grid. Well, if we can understand what the extreme ultraviolet of the sun is doing, we can know when to put our spacecraft into safe mode. We can know when to, well, pull back on the amount of energy flowing through the power grid. And this is part of why we have Solar Dynamic Orbiter. It's out there making these observations. But Solar Dynamic Orbiter, it launched 9 years ago, back in 2010, and it was only meant to go for 5 years. It's still going, it's still funded, it's in an extended mission right now, but at some point we won't have the Solar Dynamic Orbiter. And the question becomes, can we figure out another way to get at this information? And astronomers and physicists have been trying to figure out how to build physics models where, working from the first principles of science, they build the sun up and figure out, okay, so if we see this and we see this, then this thing must be happening. It's okay, but it's not completely accurate. Well, software engineers working with scientists instead took that, thank you for the bits, Wayne, instead took that full suite of images that is coming off of the Solar Dynamic Orbiter in all the different colors and said, okay, if we train a deep learning algorithm with all of this data, that when it sees these things, this is what the extreme ultraviolet image looks like. Can the deep learning, machine learning algorithm figure out how to predict what the sun is doing in the extreme ultraviolet? And the answer was yes. Magically, yes, it can. And I feel okay using the word magic, because magic just is any technology sufficiently advanced that we don't fully understand it. And the thing about deep learning algorithms is we don't fully understand how they do all the things they do. These algorithms are able to key in on things that the human mind just isn't keying in on and say, okay, if these things are here, then this. And right now, this deep learning algorithm, which was published in the most recent journal, Nature, it's able to accurately predict what the Solar Dynamic Orbiter is going to see in the extreme ultraviolet. This is one of those results that starts to show us, well, just what is possible by extending out what we do with computers, and that sometimes computers are smarter than we are, which is a bit disturbing. This is, after all, how you get Cylons. Now, this is just a start, but this is an important start because it tells us when we don't have extreme ultraviolet instruments, we can still keep our spacecraft safe, which is cool. And speaking of keeping spacecraft safe, the Juno mission has been out orbiting Jupiter in a 53-day orbit since it arrived at Jupiter back in 2011. Now, it was originally planned that once Juno got into orbit and settled in and did a mission checkout, that it would lower its orbit into a 14-day, much faster orbit. But there were concerns about the onboard engines, and it was decided for the safety of the mission that it would be best to just, well, take these longer orbits. And all of the science that Juno had planned to accomplish can still be done with this different pattern of going around and around Jupiter that is what's currently going on. Now, the thing is, Juno is a solar-powered spacecraft. And over time, as Jupiter has orbited, as Juno has gone around and around Jupiter, the alignment between the orbit, Jupiter, and the Sun has slowly changed. And the way its orbit is set up, Juno whips past Jupiter when it's close in, and then lingers and passes slowly around Jupiter when it's further out. This is a completely normal orbit, but it was also going to be a completely deadly orbit to this spacecraft because that alignment of the Sun, Jupiter, and Juno's orbit had altered over time such that Juno was about to spend 12 hours lingering in the shadow of Jupiter. And since Juno's solar powered, that 12 hours had the potential to be deadly to this particular spacecraft. During those 12 hours, Juno, the batteries would have worn down, the system would have cooled off, and there would be no more Juno on the other side of that 12-hour passage through shadow. So, to avoid that fate, between September 30th and October 1st, they fired the engines on board Juno for 10.5 hours. During that time, they accelerated the spacecraft by 126 miles per hour. And I'm looking to see what that is in kilometers. 126 miles per hour or 203 kilometers per hour. They burned through 160 pounds of fuel or 73 kilograms of fuel. And because of the burn they did, instead of passing through Jupiter's shadow, they're going to glance right along the edge of that shadow. And in the animation I'm showing you right now, you can just make out a yellow dot on the edge of this illustration of Jupiter. Well, that yellow dot is meant to represent the Sun, and you can see it pass just right next to the edge of Jupiter. This means that, well, Juno's going to have some fabulous views of the Sun just peering around the edge of Jupiter, with Jupiter largely silhouetted. Now, I don't know if they're planning any fabulous images, but, well, I'm hoping. So here is congratulations to the team at Juno for a successful engine burn, for entering a new orbit, and for keeping the spacecraft safe to do science for another day. And we have one final story for you, and this one comes to us from Mars. The Mars seismograph is incredibly sensitive, and what it's, well, watching, listening, sensing for is vibrations inside the red planet that are driven by Marsquakes, landslides, asteroid impacts, all those kinds of things. But this seismograph is so sensitive that it can hear a variety of other noises, including the dings and pings that the enclosure of the seismograph makes as it contracts and it expands when the sun comes up and the sun goes down with the thermal fluctuations. These are the same noises that you might have heard your stove make when you turn it on and heat it up. And NASA has edited those files out so that we should be able to listen to them. So this is the sound, if this works, of the thermal contraction of the enclosure around InSight. I'm not seeing any noise. There, wait, no, that's me. There it goes. So that was the noise from Mars, from the enclosure of the InSight seismograph. Now, in addition to that noise, and here I'm going to put on monitors so I can hear it as well, they were also able to detect two separate earthquakes, or in this case, Marsquakes. And they were quite small. They measured in at just 3.3 and 3.7 magnitudes. But we can nonetheless listen to them. And the way they work is radically different from the way earthquakes here on Earth work. They're more similar to the moon. Here on Earth, when our own planetary surface flexes, moves, cracks, for whatever reason, all those spaces get filled in quickly with water. We're a very wet world. Well, on the moon, where we've previously been able to detect quakes, when the moon's surface cracks, it doesn't exactly have any water to fill in. And this actually changes how the world vibrates during a quake of some sort. And the quakes end up being much more prolonged because the waves can't move straight, but instead end up bouncing around these cracks. Well, Mars has that same problem of being dry, of fissures not filling in. And so the world tends to ring more with these quakes. So let's listen to the first one. Yes. This is very lame, I'll admit to that. Okay, let's listen to the other one. Okay, so it's nothing to write home about. I don't think it's the kind of thing that you're going to be sampling and necessarily adding into your next great hit record. But it's sound from Mars. So there's that. And that's all we've got for today. I am now going to take your questions and while you type them in, I'm going to remind you to please use the purple star emote to denote where your questions are to make it easier for me to find them. This is Dr. Pamela Gay. I am Dr. Pamela Gay, and this is The Daily Space. We come to you most Mondays through Fridays, live right here on twitch.tv to bring you a quick rundown of all that is new in space and astronomy. Next week, I am going on vacation. And Annie is working on, well, battening down the hatches and keeping everything else around here going and dealing with a bunch of other stuff. So we are going to take the week off recording these episodes, but if all goes well, I will still be producing the podcast version of the show, so please check that out wherever you get your podcasts. We are produced by Susie Murph, and we are a production of the Planetary Science Institute, where I am currently located in Tucson, Arizona. The Planetary Science Institute is a 501c3 nonprofit, and we're dedicated to exploring this solar system and beyond. So we are brought to you by you. These episodes we're able to put these together and pay our folks a living wage thanks to your donations, your bits, your patronage over at patreon.com. Your subs, well, they keep us going. So thank you for everything that you do, and we're going to keep trying to do what we do. And right now what we do is answer questions. So I'm going to answer questions. Scrolling back to see what I can see. I love how you know just from the lack of audio that it must be me. Yeah, at least I'm consistent in how I fail. Oh, I'm sorry, Gita, that you have a cold. Please get better quickly. Hello, Enigma. Yes, Tucson is an unusual location, but it's one that we tend to come to fairly often. Susie, Annie, and I all work for the Planetary Science Institute, and this is where corporate meetings end up, and I come out here periodically to collaborate with folks locally. Looking to see what else is going on. Hello, all the new humans. New humans are totally welcome. Thank you for the bits, Wayne Johnson. Thank you. So Henny asks, if you know how hot a spot on the sun is, why couldn't you guess what ultraviolet is doing because of black body radiation? So let me see if I can explain the background to this question a little bit. Warm objects give off light in a whole distribution of colors that are based on the temperature of the object that's giving off the heat. When you turn on an electric stove, the temperature that you see the burners get are related to the temperature that you're heating your stove up to. They'll get more and more orangey and then yellowy as it gets hotter and hotter. Cooler things are red, hotter things are blue. Now, that's not the only way that light gets given off, however. If you have specific hot gas, it may emit all of its light only in specific colors related to the energy levels of electrons in the atoms of that gas. And this is what we start to see in the sun, where we're not dealing with thermal radiation, black body radiation. What we're dealing with instead is energy coming out of specific atoms at specific temperatures. We're also dealing with black bodies that don't necessarily give off enough energy to be detected with the diffuse gas in the corona. So this combination of problems means we can't always just look at the other colors to figure out what's going on in the extreme ultraviolet. This is why we need to have spectrographs. It's what allows us to see the specific workings. It's why we filter our images. All of these things help us build up a more complicated picture, and it's in those details that we're able to figure out what's going on. So Henny also asks, do they run simulations for the Jupiter-Juno system every few months to look out for these dangers? I assume you're talking about like passing through the shadow of Jupiter. They can actually run it and look at things for years at a time. When they initially planned this mission, they didn't think they were going to be staying in this orbit. And since they didn't think they were going to be staying in this orbit, this wasn't a problem as they had to plan for initially. But since identifying the problem, they've been waiting for just the right moment to do this engine burn. And that right moment was now. So they know what's going on very, very far in advance and can even figure these things out before launch They just couldn't figure out they were going to have an engine problem before launch. And so it's really kind of amazing what all they've accomplished. Sorry for the sneeze. Okay, looking to see what other questions are here. So Larry asks, how much frequency and time shift were in the audio from Mars? So I have to admit the place that I'm looking doesn't say. So since it doesn't say, I can't tell you. I just know that it's been shifted. I'm not sure the time was shifted. I think it's just the frequency was shifted. Yeah, I'm sorry I couldn't get you more volume. That is the best I could do. Thank you for the bets tracker, Kev. Thank you. Looking for more questions. So Rodrigo Greca says, where can we hear that audio? So it's all on SoundCloud, and NASA didn't realize that sometimes you need to moderate things. So I'm sorry for the comments. There are racist comments in this audio. Yeah. Anyways, the audio is all embedded in this press release. Thank you for the well wishes on my sneeze. So Veronica asks, are they generating the squiggly lines for Marsquakes like they do for Earth? Yes, but they're not doing it with a pen. The seismographs we have on the Earth, quite often the way they work is the machine is super sensitive such that a pen on a very fragilely balanced wire is set to wild oscillations when the Earth oscillates. They're doing everything digitally, no pen required. Hanny asks, are we waiting for an asteroid strike to find out more about Mars' interior? We're waiting for something to happen. So in order to find out about Mars' interior, we are going to need to see more and more earthquakes. And these can come from landslides, from impacts, and we don't know if Mars does or does not have its own Marsquakes that are generated due to some sort of tectonics inside the world. Now, we don't think that this is a geologically active world, but part of the reason we're doing this research is to confirm that. So we'll take any world rumbling event we can get to be able to make the seismographic measurements. Okay, so that is all the questions I see for today. Now, I am going to very quickly, before we have a staff meeting in half an hour, work to put together the podcast version of this episode. I will be back here tomorrow, and we will also be doing Astronomy Cast tomorrow. So the science is just going to keep coming, and tomorrow's Astronomy Cast is going to be a special double feature since I'm taking a vacation next week. So yeah. Is going to be the expansion of the universe and the age of the universe, discussed in detail about how we still don't know those answers. So I am going to raid Oh Bother and run the credits. I think I'm going to run the credits. I think I have the window to roll the credits. I'm going to find out in a moment. I do not, but I can open it. I'm borrowing monitors, so I still have my multiple screen setup. It is excellent. This is one of the fabulous benefits of working at a very technologically capable place. This doesn't always happen at universities where there's a scarcity of equipment. So I am now going to roll the credits and raid Oh Bother. But before I do that, I'm going to remind all of you that This is the Daily Space, and I am Dr. Pamela Gay. We come to you most Mondays through Fridays at 1 p.m. Eastern, 10 a.m. Pacific. That is 6 p.m. London time. We also bring you the Sunday Science Hour at the same time, and launches, landings, and other special events as they happen. In addition to our own programming, we also simulcast the Weekly Space Hangout and the Astronomy Cast episodes right here. So you don't need to go searching around on YouTube to find your content. Just watch here. We are part of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are brought to you by you. We are so grateful for all of your donations, your bits, your subs, and your patronage over at patreon.com. If you want to help us out and you want to do something other than sending us money, that's cool. We're good with that. If you can please get the word out, let people know we've got a podcast. We are here live, and you can find all of our archived episodes over on YouTube. Subs are free over on YouTube and on your podcast player. So give us a sub, give us a share, and help get science out into the world. And that's all I've got. Wherever you are in the world, have a fabulous morning, evening, or afternoon. And I'll see you on the other side. Bye-bye.